Hello physics students. In the last video, I explained how there are only 4 forces in the universe, and that one of those is the force of gravity, and that's what we're going to be studying in this unit. Now specifically, we're going to be studying how we can determine the magnitude of the force of gravity and also how we can determine the motion of objects under the influence of this force. Now, if the objects go a very small distance compared to the magnitude or the size of the Earth, and by the way, the motion, when I say small, could be something like a cannonball shooting like all the way across the Hudson River. It could be like miles. But on the global scale, even when I shoot a cannonball, I wouldn't even see that moving on this global scale. So that's what I mean. Small is like a relative term. Then we can pretend the Earth is flat in that case. And that's what we're going to be doing for the first week of this topic. Then we're going to take a step back and we're going to look at the motion that's larger. And when something is shot maybe from continent to continent or going into outer space, then we're going to finally have to contend with the fact that the Earth is not flat, it's round. And then we're going to learn about the gravity, how it behaves, and also the motion. And then there's part 3, which I mentioned briefly, is Albert Einstein's wonderful, amazing theory, beautiful theory, that there's no such thing as a force of gravity. The Earth or any mass warps space and time around it, and that warped space and time causes these paths that look curved but are really straight in the curved space-time. So that's the 3 levels of gravity, but today we're focusing, as I said, for the first week on the small motion, small in quotes, where we can assume the Earth is flat. Now, why can we assume that? Because whenever our objects are moving for whatever range, as they're going up, the force of gravity does not change by enough for us to notice. So it doesn't change with altitude, it doesn't get weaker like it truly does. So we can't detect that weakness, so we could pretend it doesn't get weaker. And then also as we displace sideways, the direction doesn't change, which is definitely not true. But again, on the small scale of the motion, it's 99.9999% true. So that is what we're focusing now, this small motion. And because of those facts about the force of gravity, there are 2 things that are true for these projectiles, 2 facts. They are the heart of this week of projectile motion. And hopefully you know what they are. You better know what they are, because if you don't know what they are, you're going to be tripped up and going to be getting questions wrong all week. So what I'm going to do is create a pause now. And in that pause, you're going to quiz yourself mentally. Try and think of these 2 ideas. If you can't, then slap yourself on the wrist, look back in your notes, and study them before you go on. So here's the pause. Okay, so hopefully you knew what they were. And if you didn't, then you know them now. Which is that in the vertical direction, which is the way the force of gravity works, there's an acceleration of negative 9.8 in the y. In the x direction, horizontally, because gravity doesn't act horizontally, the acceleration is 0. In other words, the velocity is constant. Acceleration 9.8, 0 acceleration, constant velocity. Those are the 2 facts, okay? They're independent of each other. So even if you throw something sideways, the acceleration doesn't stop. Even when something's falling, the velocity doesn't stop. And that's the heart of this topic, okay? Now, in the last video, I had this little Excel file, and I showed how those 2 facts generate the motion of a projectile, a parabola. And I could figure out that motion through iteration of calculation after calculation. But that's not a convenient way to figure out the motion of these things, these projectiles, because what if the object's motion doesn't last an exact number of seconds? In other words, what if the ground doesn't hit, the projectile doesn't hit the ground at exactly 5 seconds, but 5.1 or 5.7? What we did yesterday or in the last video will not work. So that's the topic of this video. The actual way we solve these projectile problems. So in the last video, it was mostly concepts. This is how you're going to be answering questions on the quiz and on the Regents and on the test. So let's begin. Horizontally launched projectile calculations. Here's the problem. A stunt driver drives off a 35-meter tall cliff. Maybe there's like some kind of scene in a movie with a car crash. And he's going 30 meters a second, which is over 60 miles an hour. Determine the time to land, the landing location, and the velocity on impact. So here's a little sketch of what's going on. We got this cliff 35 meters tall. Car comes off, goes like this, and makes this parabolic path, crashes right here. Maybe we want to put the little padding here out of view so that, you know, they don't see it in the movie, but the stunt driver survives. So where are we going to put this little landing pad for the stunt driver? We need to know. So we're going to calculate it. So remember, projectiles are two things happening at once, two kinematic problems happening at once. Now, again, here's a little warning. I mentioned it in the last video. Projectile problems are not easy. Remember, we had kinematics, Unit 2, and people had a lot of problems with those, a lot of difficulty with those problems. Now what's happening here are two problems happening at the same time. So what's harder than one problem? Solving two at the same time, right? So here we go. We have to think Y direction and X direction, two different problems. So the first thing you have to realize, the time to land is determined by how tall the cliff is, not how fast you're going horizontally. Think of this, if this is a little tiny hill, it hits the ground right away. If we go off of a cliff like Mount Everest, it's going to take minutes to hit the ground, right? So the height is what matters. So when we're solving for time, it's a Y direction, right? Y direction calculation. So what we're going to do is list all the information that we know about the Y motion. That, for example, the distance in the Y direction is 35 meters. And that the acceleration in the Y direction is negative 9.8. We knew that, okay? But here's the tricky thing. V initial 0. People say, I thought it was 30. How could it be 0? And that's, again, the difficulty. Two problems happening at once. Some data applies to the X problem. Some data applies to the Y problem. You cannot mix them up or you get the wrong answers. This is, as we could see in the picture, completely in the X direction. This is driving off a cliff like this, so it doesn't enter into the Y calculation. If there was a ramp shooting this car upward or downward, okay, now we have a Y velocity initial. But no, we have horizontal, no Y velocity initial. And we're looking for the time. So what we do is we grab a reference table and we look for a formula that has those variables, d, acceleration, v initial, and time. So we're back in the mechanics section here. At the top, the kinematics formulas, and what you could see is that the formula that has those variables is d equals vit plus 1/2 at squared. Familiar formula. So let's start by jotting that down. So here it is. Here's the formula. Now, as I mentioned when we were studying kinematics way back in September, is that if this part of the formula is 0, you could not only just cross it off, you don't even have to write it. You could have just wrote down d equals 1/2 at squared, and you would lose no credit. Any part of the formula is 0, you could just leave it off. All right, so let me give you a moment to pause for you to catch up if you need it. Okay, so now the next thing we do, of course, is we plug in our data. So that's over here. Now, 35 meters, 1/2, negative 9.8 t squared, with the units, of course. Now, here's the thing. If you try and solve this, you're going to get a negative under the radical. So I left the minus sign off on purpose to explain that, yes, you have to consider minus signs. If the gravity is down, the motion is down. So if I want to call this negative 9.8, I've got to call the 35 meters negative 35, because it's down too, and I have to be consistent. As an alternative, I mentioned in the when we were studying kinematics, you could have left them both off, and it's fine, and you don't lose credit. But if you want to stay strict with the signs, both negative. So you divide both sides by 4.9. That's where the 7.14 comes from. Take the square root of both sides, you get 2.67. There's the time for that stunt driver to crash into the ground. The next thing we're looking for is the landing location. So like, how far from the base of the cliff is this car going to strike? So it's a new kinematics problem. I got to start all over laying the variables out. And notice right away, VI is not 0 now. It was 0 over here. See how hard that is? 0 one place, not a 0 another. Oh man, it's going to get confusing. Well, that's why we're going to be practicing with so many of these projectile problems so that you're not only going to get sick of them, you're going to get great at them, hopefully, right? So that's the goal. So VI is 30 because VI is all in the x direction. Acceleration was 9.8 over here. Here it's 0. Gravity doesn't act sideways, it acts down. So if we're going x direction calculation, we got to say 0 acceleration. But we do know that the x motion ends when the car crashes into the ground, so the 2.67 does go from the y to the x. And we're looking for the x direction displacement. So once again, we take out our reference table, we look for a formula, and it's the same formula, d equals VIT plus 1/2 AT squared. But whereas here we cross the VI in the y calculation, here there's no acceleration. You could write out the formula and cross it out, or you could have just not even bothered writing this in the first place, and you would lose no credit at all if you just wrote d equals VIT. Plug in the VI, the time, and you get the distance horizontal displacement. So that's how far from the base of the cliff. So it's really like stretched out motion. If this is 35, 80 is like somewhere over here. All right, so let me create a pause and allow you to catch up if you need to. One last part, the velocity of impact. So I'm going to make some room here. Okay, so what I have to realize for part C is I'm going to just draw the motion over here again. So this, as I said, this is 35 meters, but I'm not even going to write that because that's just going to add more data that's going to get confusing. The car goes something like this, boom, lands over here, 80 meters this way. So when it impacts, it's got a velocity something like this. That's the velocity I'm looking for. But I have to realize that that actually has components to it. There's an x component, right? If I make a dotted line like this, there's an x component like this. And there's a y component. If I make a dotted line like this, oops, well, kind of crooked, but hopefully you get the idea. There's the y component of the velocity. What I have to do is find both of those. But the x part is easy. If the thing went off the cliff at 30, it's 30, 30, 30, 30 the entire time sideways because there's no acceleration in the y direction. So right away, I have one of them. Vx equals 30 meters per second. But the y part, it's accelerating. So what I have to do is I have to basically solve out from this. V final equals V initial plus AT. Now remember, the VI was not 30. That was for the x. For the y, it was 0. I'm in the y direction here, right? So, you know, this looks a little, maybe I should have done this. Hopefully I didn't mess you up too much. X. And then say that this is V equals 30 meters per second. And then in the y, I'm going to do V final equals V initial plus AT, as I said. So this was 0, as I mentioned. So now I'm going to plug in negative 9.8 for acceleration for the y direction and the 2.67 seconds. Boom, 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 hit it on the calculator, and I get 26.2 negative. And maybe I'll call this Vy and Vx now. So this is negative 26, or 26 down. This is 30 sideways. How do I find this? I'm going to use the Pythagorean theorem. Now, because, right, I have a right triangle here, 26 and 30. So how do I find this? Pythagorean theorem. Now, in this, for the sake of, you know, just being quick, I'm not going to write out the Pythagorean theorem. I'm just going to put, right, because first I got to write a formula, always on the Regents. I'm going to skip that just basically because I don't want this video to be too long. So the x part is 26.2 plus the y part. And so I add these up, take the square root, and that gives me some velocity. Again, whatever it is, you got to punch it on a calculator if you wanted it. The angle, right? So I might want to know the angle because if I'm asking for velocity, I want not just the magnitude but the direction of the travel also. So to find that, I could use a trig function. I could use tan theta. This is again 26, this is 30, so I got the opposite side and the adjacent side. Again, I'm going to skip writing out the formula just so I could be as quick as possible here. So tan theta equals 26, the opposite side, right? That's over here, the opposite side, which is the y component, right? 26, oops, I forgot the 0.2. And the adjacent side is right here, the 30 of the x component. So 30 meters per second. I divide this, then I do the inverse tan, and I get my angle. So that's how you solve this problem. All right, I'll create a pause to allow you to catch up and write this down. Okay, maybe I should get my stick out. Do you know the 2 facts about projectiles, right? Hopefully you do, right? But here they are. I'll remind you again. In the x direction, 0 acceleration or constant velocity. Same thing, saying 0 acceleration or constant velocity. In the y direction, there's an acceleration of 9.8 in the downward direction. So those are the 2 facts, constant velocity, constant acceleration at 9.8. And those 2 things happen at the same time, creating this motion, which means when you're solving a problem, you've got to have 2 separate calculations, at least one for the y, one for the x. In the y, I erased it, but what you have is d equals 1/2 at squared, because this was 0, but this was not in the y, d 1/2 at squared. In the x, this is now 0, so you have dx vit, okay? And keep the data separate, solve away, okay? So that is how you calculate the various things of a projectile going like this. All right, I hope you enjoyed the calculations, and I hope you enjoyed the video. I'll see you in the next physics video.